Hello everyone, we are going to learn about some theorems on Coset. Theorem 1. If H is any subgroup of G and H belongs to H, then right coset HH is equal to H is equal to left coset HH. Proof. Suppose H belongs to H. To show that right coset HH is equal to H, we have to show that H is contained in H and H is contained in HH. Suppose H dash is any arbitrary element of H. Then H dash H is an arbitrary element of HH. Since H is a subgroup, we have H dash belongs to H and H belongs to H implies that H dash H belongs to H, since H is subgroup and it is closed. Thus, every element of HH is also an element of H. Hence, right coset HH is subset of H. Again, H dash is equal to H dash E is equal to H dash H inverse H, since H inverse H is equal to identity element of the group. This is equal to H dash H inverse H by associativity. This belongs to right coset HH. As H belongs to H implies that H inverse belongs to H, and H dash belongs to H inverse belongs to H implies that H dash H inverse belongs to H. Thus, every element H dash of H is also an element of HH. Hence, H is subset of right coset HH. Therefore, HH is subset of H and H is subset of right coset HH. This implies that HH, right coset HH is equal to H. Similarly, we can show that left coset HH is equal to H. Hence, right coset HH is equal to H is equal to left coset HH. Theorem 2. If A, B are any two elements of a group G and H any subgroup of G, then right coset HH is equal to HB if and only if A into B inverse belongs to H, and left coset AH is equal to left coset BH if and only if A inverse B belong to H. Proof. Since A is an element of right coset HH, therefore HA is equal to HB implies that A belongs to HB, implies that A into B inverse belongs to HB into B inverse, implies that A into B inverse belongs to H into B inverse. This implies that A into B inverse belongs to H, since B into B inverse is equal to identity element of the group E. Implies that A into B inverse belongs to H. Therefore, HA is equal to HB implies that A into B inverse belongs to H. Conversely, suppose that A into B inverse belongs to H. We have to show that left coset HA is equal to left coset HB. Now since A into B inverse belongs to H, so H into AB inverse is equal to H. By the property, as H belongs to H implies that H into H is equal to H. This implies that H into AB inverse into B is equal to HB, operating with B on the right side of the expression. Implies that HA into B inverse B is equal to HB by associative property of the group. Implies that HA into E is equal to HB, and implies that H is equal to B since A into E is equal to A. So left coset HA is equal to HB. Similarly, we can prove that left coset AH is equal to BH if and only if A inverse B belongs to H. Theorem 3. Any two right or left cosets of a subgroup are either disjoint or identical. Proof. Suppose H is a subgroup of a group G, and let right coset HA and right coset HB be two right cosets of H in G. Suppose HA and HB are not disjoint. Then there exists at least one element, say C, such that C belongs to HA and C belongs to HB. Let C is equal to H1A and C is equal to H2B, where H1, H2 belongs to H. Then C is equal to H1A is equal to H2B, implies that H1A is equal to H2B, implies that H1 inverse H1A is equal to H1 inverse H2B, operating both sides by H1 inverse, implies that EA is equal to H1 inverse H2B, since H1 inverse H1 is equal to identity element E. So this implies EA is equal to H1 inverse H2B, implies that A is equal to H1 inverse H2 to B. Since H is a subgroup, therefore H1 inverse H2 belongs to H. Let H1 inverse H2 is equal to H3. Then from here we have A is equal to H3B. Now HA is equal to H3B is equal to HH3, B is equal to HB. Since H3 belongs to H, implies that HH3 is equal to H. So HA is equal to HB. Therefore, the two right cosets are identical if they are not disjoint. Thus, either HA intersection HB is equal to phi or HA is equal to HB. Similarly, we can prove that either AH intersection BH is equal to MT or AH is equal to BH. Theorem 4. If H is a subgroup of a group G, then G is equal to the union of all right cosets of H in G. That is, G is equal to H union HA union HB union HC up to ... where A, B, C dot are elements of G. Proof: G is a group. Therefore, each element of any right coset of H in G is an element of G. Hence, the union of all right cosets. Hence, the union of all right cosets of H in G is a subset of G. Also, if X is any element of G, then X belongs to Hx. Therefore, X belongs to the union of all right cosets of H in G. Hence, G is a subset of the union of all the right cosets of H in G. Symbolically, we have G is equal to union Hx, X belongs to G. Similarly, we can prove that G is also equal to the union of all left cosets of H in G.